safer battery monitoring for hazardous environments. Battery infrastructure is under increasing scrutiny as energy systems scale and operational demands intensify. In high risk environments, particularly where explosive gases may be present, the margin for error continues to narrow. A newly introduced intrinsically safe battery monitoring module, the DCM6L IECEX from Parameter, reflects a broader move towards safer, more integrated approaches to managing these risks. Designed for Zone 1 and Zone 2 environments, the system incorporates intrinsic safety at the design level rather than relying on external protective enclosures. This approach aligns with IECX requirements while reducing system complexity and physical footprint, two factors that often complicate deployment in constrained or hazardous settings. Moving beyond reactive maintenance, battery reliability has long been a concern in mission-critical infrastructure. In hazardous locations, failures carry added consequences, including the potential for ignition in gas-prone environments. Traditional maintenance approaches have relied heavily on manual inspections, requiring personnel to enter these areas to identify faults. The DCM6L IECX introduces continuous monitoring at the cell level, capturing metrics such as voltage, temperature, and internal resistance. This enables earlier detection of performance issues and supports a shift toward predictive maintenance strategies. By identifying faults before they escalate, operators can reduce unplanned downtime while limiting the need for routine entry into hazardous zones. Maintenance teams are able to respond with more targeted interventions, improving both efficiency and worker safety. Over time, this can lead to fewer site visits, faster issue resolution, and more controlled risk exposure. Designing for compliance and simplicity. A notable aspect of the system lies in its design methodology. Instead of retrofitting safety features onto existing equipment, the module is engineered to meet intrinsic safety standards from the outset. This removes the need for additional enclosures or layered certification processes that can add cost and complexity. Installation is streamlined, with the unit designed to integrate into standard battery configurations without requiring structural changes. Pre-certified components, including leads and probes, further reduce setup time and eliminate the need for ongoing calibration, typically associated with more complex safety systems. For operators managing distributed or large-scale infrastructure, these design efficiencies can translate into lower lifecycle costs and reduced maintenance burdens, while maintaining compliance with evolving regulatory frameworks. Converging pressures across industries. The introduction of intrinsically safe monitoring systems comes at a time when the boundaries between traditional energy sectors and digital infrastructure are becoming less distinct. Industries such as oil and gas have long operated in hazardous environments, but similar conditions are emerging in data centers as energy storage systems expand to support high-density computing. As battery deployments grow in scale, so too does the potential for gas emissions and thermal risks. This has prompted closer alignment with standards like IECX, which are gaining broader adoption across regions and industries. At the same time, the market for hazardous area equipment is expected to expand, driven by increased demand for compliant and scalable safety solutions. In this context, intrinsically safe battery monitoring represents a shift toward more proactive risk management. Rather than treating safety as an add-on, operators are integrating it directly into system architecture, balancing compliance, operational efficiency, and workforce protection as energy storage becomes more central to infrastructure strategies.